Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Imagine yourself lying on a soft meadow on a clear night, far from any city lights. The air is cool against your skin, carrying the faint scent of grass. Above you, the sky is a black, velvet dome sprinkled with countless stars. The Milky Way arches overhead, a pale river of starlight. In this quiet moment, you feel deeply connected to the cosmos. The same space that stretches between those stars also surrounds you. A gentle breeze brushes your cheek. It moves through the night and through the space around you, here on Earth. As you gaze upward in comfortable silence, more and more pinpoints of light emerge, a glittering mosaic against eternity. You realize that when you look at these stars, you are literally looking back in time. Their light has traveled for hundreds or thousands of years to reach your eyes tonight. Some of those stars may have already lived out their lives and vanished, yet their glow still journeys onward through the dark to greet you here and now. You feel the solid earth beneath you and know that it too is suspended in that great darkness, a small, warm world afloat in an ocean of space. Yet you are not afraid. The darkness above feels inviting, almost comforting, like a vast shelter. The endless sky, rather than making you feel insignificant, fills you with peace and wonder. In the silence, you sense with gentle certainty that you are a part of this grand universe. The starlight that falls on your skin, the space that cradles your body, the photons entering your eyes, all of it binds you to the cosmos. You close your eyes for a moment. Behind your eyelids, the after-image of the stars dances in little sparkles. You take a slow breath in, and as you exhale, you let any tension flow out of you and into the vastness around. There is room for all of it to dissolve. There is room for everything in space. The universe is so wide and forgiving that your own cares begin to feel lighter, quieter, soothed by the infinite calm. Now, in that spirit of tranquility, let us embark on a journey into space itself. The space around us, the space within us, the space that is the foundation of all things. We begin where we are, in stillness, in the darkness, in the quiet. The night is profound and motionless. Above, the stars shine as tiny islands of light in a vast sea of black. Space stretches endlessly between and beyond them. This scene feels serene and timeless. Nothing stirs. No breeze now, no sound at all, only a gentle hush, the natural silence of a cosmos at rest. It is as though time itself has paused. You can almost feel the depth of this silence, a soft, velvety silence that blankets everything. The emptiness around you seems to embrace you with a subtle, invisible presence. For ages, we humans looked at the night sky and found it peaceful, but also mysterious. What is this blackness between the stars? We used to think it was nothing, an empty void, an infinite vacancy. People spoke of the void and the vacuum as if it were a true nothingness. We even doubted whether a true vacuum could exist at all. Ancient philosophers imagined that space must be filled with something. Aristotle believed nature abhorred a vacuum. Later, scientists in the 19th century hypothesized an invisible ether filling space to carry light across the emptiness. But experiments showed no such ether was needed. Light moves through empty space itself. This was a remarkable discovery. The void can carry light, as if emptiness has its own solidity. It hinted even then that space is not simply an inert backdrop. For a long time, though, the common view of space remained that it was a passive emptiness, a gargantuan container in which the objects of the universe, planets, stars, galaxies, are scattered. We pictured space as a stage and the stars as actors upon it, with no real influence from the stage itself. If you removed all the actors, the stage would just sit there, blank and silent. We imagined that if you took all matter away, you'd be left with pure nothing, an absolute void, infinite and eternal. Over time, however, our understanding evolved dramatically. We learned that space is far from nothing. That black backdrop, that stillness and silence, is deceptive. Space has properties, a structure, a dynamic of its own. In the past century, every new discovery has reinforced this truth. Space can bend. Space can carry light and soundless vibrations. Space can stretch. It can even boil at the tiniest scales, flickering with unseen energy. What we once thought of as an empty stage is more like a participant in the cosmic play. Tonight, as you float in this quiet moment, the darkness around you is not dead or inert. It is the very fabric that connects and supports all things. Let's explore this step by step, gently and thoroughly, starting with one of the most profound revelations, that space and gravity are intimately linked. Beneath you, the Earth's mass is pulling you down, or rather, it's warping the space under your body so that down is the direction you naturally fall. Above you, the moon is held in its orbit by the shape of space around Earth. This understanding comes from Einstein's great insight in the early 20th century. Gravity is not a mysterious force acting across empty distance, but a feature of space and time itself. Mass and energy tell space how to curve, and the curvature of space tells objects how to move. In essence, matter sculpts space, creating valleys and hills in the fabric of space-time, and objects simply roll along those curves. What you feel as gravity, the weight on your back as you lie in the grass, or the pressure of your body against your bed, is actually space itself pushing you downward, guiding you along the curved lines it has formed around the Earth. To visualize this, imagine space as a vast elastic sheet spread out under the stars. If you place a heavy object on that sheet, say a bowling ball to represent a star or planet, the sheet will dimple, sagging inward around the weight. Now, if you roll a marble nearby, representing a smaller object like a planet, the marble will no longer travel in a straight line. It will spiral around the bowling ball, caught in the curve. In reality, Earth orbits the Sun because the Sun's mass curves the space around it, creating a sort of well that Earth is rolling around. Earth thinks it's moving in a straight line, and indeed it is, locally, but space itself is curved, so straight for Earth is actually a loop around the Sun. There is no gravitational force pulling Earth in a literal sense. Earth is simply following the path allowed by the curved space, like a ball rolling around a curved bowl. All planets, all moons, all orbiting bodies are doing the same. They are not tethered by invisible strings. They are skating along the contoured roads of space. Right now, as you lie still, you are held to the ground by this phenomenon. The mass of the Earth has curved space under you such that down points toward Earth's center. Your body presses into the ground because space is telling you to move that way. The ground pushes back and holds you up. Space does this quietly and continuously. You feel the effect as weight, but really, it is space-time gently urging you along a curved path that the solid Earth prevents you from taking. If Earth were not here, that curvature would extend unopposed. You would fall freely along a path through space toward where Earth's center was. All of this happens with no sound and no drama. Space does its work quietly. In essence, what we experience as gravity is the shape of space around us. Matter, like the Earth beneath you, tells space-time how to curve, and that curved space-time tells matter how to move. Gravity is not something that reaches out through space. Gravity is space. The stillness around you, in fact, is full of these invisible curves and subtle depressions wherever there is mass nearby. If you could see the geometry of space, You'd see gentle indentations around every tree, for even small objects curve space a tiny bit. Deeper wells around the mountains, and a huge well under your body, reaching to Earth's core. But space does its job so smoothly that you don't notice anything odd. You just stay attached to Earth as naturally as a leaf rests on the ground. This idea also means that when a massive object moves, it can create ripples in the fabric of space. Much like a stone dropped in a pond sends out waves on the water. Imagine two massive stars circling each other rapidly, or better yet, two black holes, extremely dense objects, spiraling together. They disturb the space-time around them so much that waves of curvature spread outwards. These are called gravitational waves, literal ripples of space traveling at the speed of light, washing through the cosmos. For a long time, we weren't sure these ripples really existed, but in recent years, scientists built instruments so sensitive that they could feel space-time tremble. When two distant black holes collided and merged, in a galaxy billions of light years away, our detectors on Earth quivered ever so slightly. Space itself stretched and squashed by a tiny amount, far smaller than an atom, as the gravitational wave passed through. We heard the universe whisper through space-time. It was as if the stillness briefly sang a faint melody. Think about that. We built a device that can sense the movement of space from events that happened billions of years ago in far-off corners of the universe. When we detected those waves, it confirmed that space-time is not just an abstract idea. It's a real, physical fabric that can carry vibrations. Space can ring like a cosmic bell, even though we cannot hear it with our ears. In September 2015, when those two black holes merged, the fabric of space around Earth oscillated subtly, and our instruments recorded the telltale chirp. It was a triumph of human curiosity and a profound validation of the idea that emptiness has structure. The silence of space isn't absolute. If you have the right ears, space can indeed be heard. What an elegant picture, space as an ever-present elastic medium, carrying both the weight of stars and the whispers of their collisions. In summary, matter tells space-time how to curve, and space-time tells matter how to move. Gravity is not a pull through some void. It is the gentle guidance of objects along the contours of space-time. All of this, the Earth holding you, the Moon orbiting Earth, Earth orbiting the Sun orbiting our galaxy's center, is happening because space itself is shaped by mass and energy. Our everyday experience of weight is actually our intimate connection to the shape of space. So, from the stillness of space arises what seems to be a force, but space has more surprises. We've talked about space's shape. Let's now consider its unity with time. When Einstein described gravity as the curvature of space-time, he was saying something equally profound about time. That time is woven into the very fabric of space. Out in this quiet night, space and time seem separate. You can point in directions, you feel time passing. But experiments and theories show that they are inextricably linked. If you move fast or sit in a strong gravitational field, your experience of time changes relative to someone elsewhere. Space and time together form a four-dimensional weave, and gravity is the bending of that weave. Consider that the passage of time on the surface of Earth is slightly slower than time far out in space, because Earth's mass not only curves space, but also warps time. A clock on a mountain, where gravity is a tad weaker, ticks a little faster than a clock at sea level. Likewise, a clock on a fast-moving spaceship will tick slower than one on Earth. This isn't science fiction. We've measured it with precise atomic clocks. Even the GPS satellites in orbit must correct for time running faster up there. Weaker gravity, so faster time, compared to ground. Otherwise, their positioning would drift. What we find is that space and time adjust together. If space is squeezed or stretched, time is also altered. They are two aspects of a single entity, space-time. Think of space-time as a fabric with both spatial threads and temporal threads interwoven. You cannot disturb one without disturbing the other. When the sun's mass curves space-time, not only does space get warped, but time runs a bit slower near the sun compared to far away. An astronaut near a massive object ages a bit less quickly than one floating in weaker gravity. This is called gravitational time dilation. Similarly, if you travel at a speed close to light, time for you will slow relative to those you left behind. There is a famous thought experiment. Imagine twins, and one goes on a near light-speed journey to a distant star while the other stays on Earth. If the traveling twin returns after what she feels was perhaps a few years, she might find decades or more have passed on Earth. Her clock and body experience time more slowly due to her rapid motion through space-time. This isn't just a story, it's a real effect, verified by many experiments with particles and precise clocks. All of this tells us that space and time are not the separate, absolute backgrounds we once assumed. There is no universal time ticking the same for everyone, regardless of their state of motion or gravity. Instead, every observer has their own passage of time, depending on how they move through space and how space is curved where they are. Two people reunited after following different paths through space-time will have experienced different durations. What an astonishing reality. Time itself is elastic, flexible, personal. So here, under the stars, when you consider a moment of time and a stretch of space, realize they are part of one four-dimensional continuum. Here and now are bound together. You cannot point to a location in space without also specifying the moment in time. Everything that happens in space-time. The unity of space and time frames all experience. Right now, your heartbeat and the position of the moon both have coordinates in space-time, and gravity is the geometry of that space-time linking the two. Space and time are fused like two threads of a single fabric. Move fast through space, and you skew your passage through time. Stand in strong gravity, and time for you will run a bit slower than for someone far away. This interplay might sound complex, but think of it this way. Space alone isn't the full stage, and time alone isn't either. Rather, events unfold in space-time. If you try to separate them, you lose part of the picture. Even this peaceful moment has a space-time coordinate. You, here and now, under the night sky. As you lie there, time flows a tad differently than it would if you were orbiting the Earth or sitting on the moon, because the gravity and motion differ. The differences are small but real. Space-time enfolds you, ensuring that your now and here are connected into the grand tapestry of cause and effect that makes up reality. The important takeaway is, space and time are one fabric, and gravity is the bending of that fabric. The stillness you feel includes both space and time quietly doing their work. There is a timeless quality to this night because space and time together create that sensation. In this eternal present, you are embraced by space-time, which gently carries you along the stream of time while holding you in the structure of space. We have journeyed outward to see that what we thought was emptiness actually shapes the cosmos, and journeyed inward to see time intertwined with space. But the rabbit hole goes deeper. We must now explore the nature of space at the smallest scales, far smaller than a grain of sand, smaller than an atom, where an entirely new picture emerges. One might expect that if you zoom into space closely enough, you would eventually find absolute stillness and uniformity, perhaps even true nothingness. But our current understanding, through the lens of quantum physics, says otherwise. On extremely tiny scales, space is anything but smooth and still. It is frothing and fluctuating, buzzing with ephemeral activity. Physicist John Wheeler poetically called this the quantum foam. To grasp this, imagine shrinking yourself down beyond the microscopic, beyond the level of atoms, to a realm billions of times smaller. If you could stand there, if the word stand even makes sense at that scale, the tranquil emptiness you perceive at our scale would vanish. Instead, you'd witness space seething with spontaneous eruptions of energy. Particles would blink in and out of existence like fleeting sparks. Distances and directions would blur as uncertainty reigns. In quantum physics, even what we call a perfect vacuum, completely devoid of matter and cooled down to remove all heat, is not truly empty. There is a fundamental jitter that cannot be removed. This is because the laws of quantum mechanics tell us that certain pairs of physical properties, like energy and time, or position and momentum, cannot both be known with infinite precision. There is a built-in uncertainty, and because of it, a vacuum cannot have exactly zero energy for all time. If it did, we'd know both its energy, zero, and that it stays that way, no fluctuation, forbidden by quantum rules. Instead, the vacuum seethes with what we call zero-point energy, a baseline, irreducible energy. What does this mean in practice? It means that empty space is constantly witnessing tiny particles flickering into being from nothing, then vanishing almost immediately. These are often called virtual particles. For example, a particle of light, a photon, might momentarily pop into existence, along with a counterpart, perhaps an electron-positron pair, borrowing energy from the vacuum for a brief instant. They appear, exist ever so briefly, and then annihilate each other, paying back the energy. All of this happens on timescales and distances so small we normally have no way to detect it directly. But it's happening everywhere, all the time. The space around you, between you and the next breath of air, between the electrons and nuclei in your body, between the Earth and Moon, is awash in these quantum fluctuations. On the scale of the unimaginably small, much smaller than an atom's nucleus, space-time would not look like a smooth sheet. It would look like a turbulent ocean surface in a storm, full of random waves, bubbles, and wrinkles, hence quantum foam. One moment, a bit of space might have slightly higher energy, sprouting a virtual particle-antiparticle pair. An instant later they collide and disappear, leaving a slight vibration of energy that then might spawn another pair elsewhere. Space at that level is a riot of spontaneous activity, an invisible, high-speed flickering that averages out to a seemingly smooth, stable whole at larger scales. We've even observed tangible effects of this quantum vacuum. If you place two metal plates extremely close together in a vacuum, just a few nanometers apart, they will experience a tiny force pushing them toward each other. This is the Casimir effect, and it happens because the quantum foam between the plates is slightly different from the foam outside. Certain virtual particle wavelengths can't exist in the narrow gap, so there is a tiny imbalance, fewer electromagnetic modes between the plates than outside. The result is a subtle pressure that nudges the plates together. In essence, the empty space between the plates has less quantum activity than the space outside, causing them to be pushed inward by the more energetic fluctuations outside. It's a small force. You'd need sensitive instruments to measure it, but it's real and has been observed. It's as if the vacuum between the plates is not nothing. It exerts a gentle push. This is a direct demonstration that empty space is never truly empty. The vacuum is alive with energy and possibility. In particle physics experiments, we also see clues of the quantum vacuum. For instance, empty space can briefly lend energy for the creation of particle pairs that affect processes like nuclear decay. The very fact that protons and neutrons inside atomic nuclei can change forms via quantum fluctuations involving ghostly particles is tied to vacuum activity. Even the stability of atoms and the patterns of atomic spectra bear the imprint of zero-point energy. So, as incredible as it sounds, the takeaway is that emptiness is not truly empty. It's an active medium. The stillness we perceive is actually a frenetic dance at microscopic scales. The vacuum is constantly borrowing energy here, giving it back there, in accordance with quantum uncertainty, Put poetically, even when nature whispers hush, there remains an undercurrent of subtle noise, a quiet fizz of existence and annihilation on the tiniest scales. The concept of nothingness has been forever changed by this discovery. Empty space is a cauldron of potential, a field of fields, a stage for ceaseless miniature drama. If you were to shrink down into that realm, as a moment's imagination, since physically we cannot, you might see space flicker with tiny flashes, the foam that Wheeler described. It wouldn't be placid or uniform, it would be dynamic and random. The notion of a sharply defined point in space might lose meaning, blurred by these fluctuations. We sometimes say space-time becomes quantum foam at the Planck length, about 1035 meters, far smaller than any particle. At that scale, the smooth geometry of space-time breaks down into something probabilistic and fluctuating. Let's take a different kind of imaginative journey to appreciate this. Inward, into the fabric of matter and space inside you. Envision shrinking yourself, as we did under the stars, but now not in distance outwards, rather in size. You diminish down past the scale of dust mites, past cells and their nuclei, past even viruses and DNA molecules. Now you are smaller than an atom. Ahead of you floats a single atom of carbon from your body. It appears enormous from your current perspective. You approach it like a tiny spaceship nearing a planet. The atom consists of a blurry sphere, that is the cloud of electrons orbiting the nucleus. As you draw closer, this cloud is mostly transparent. You realize the electrons are tiny points moving so fast, they form a diffuse shell. You dive through this wispy shell of electron probability and find yourself in the interior of the atom. Suddenly, you are in what seems like a vast cavern. It feels eerily similar to drifting in space between stars. It is dark and almost empty. You might even see a faint glow of energy fluctuations around. The quantum foam flickers here too. For a moment, it's as if you're floating in a miniature version of outer space, a huge volume with almost nothing in it. Ahead, after some distance, you see a tiny but brilliant object, the atomic nucleus. You move toward it. What before was the immense atom is now mostly behind you. All that's left ahead is that nucleus, a cluster of protons and neutrons tightly clumped. It's small, incredibly small. If the whole atom were a cathedral, the nucleus would be like a single grain of sand at its center, and yet, that grain of sand holds almost all the mass. You come right up to the nucleus. It's made of particles bound together, busy with internal motions, but you cannot linger. At this scale, forces are intense. You decide to zoom back out. When you return to human scale, you carry with you a profound appreciation. Inside every atom in your body, between the electrons and the nucleus, there are enormous stretches of empty space. In fact, nearly all of the volume of each atom is empty. The solidity of your body, of the ground, of this meadow, it's an illusion created by the electromagnetic forces of electrons repelling each other at those tiny distances. No two atoms ever truly touch in a physical sense. Their electron clouds push against each other first. Matter is a scaffold built on emptiness. It is astonishing. All the solid things we see around us are about 99% empty space. If one could magically remove all the empty space within the atoms of your body, compressing the electrons into the nuclei, you would shrink to a microscopic speck, smaller than a pinhead, yet you'd weigh the same as you do now. By some estimates, if we removed all the empty space from all the atoms of all humans on Earth, the entire human race could fit into a volume the size of a sugar cube. It sounds impossible, but it's because atoms are so vast compared to their tiny nuclei. Nature itself offers a demonstration. In neutron stars, the remnants of large stars, gravity crushes atoms so hard that electrons and protons merge, eliminating that atomic emptiness. A single teaspoon of neutron star material can weigh billions of tons. That's how much stuff was hiding in the empty space of atoms. When that space is removed, matter's true density shows. Fortunately, here on Earth, our matter stays spacious, our atoms intact with their generous voids inside. Take a moment to let that sink in. Solidity is an illusion. When we say an object, a rock, a chair, your own body, is solid, we're talking about the collective sense of touch that arises from trillions of atoms whose electrons resist being pushed into the empty space of one another. It is like a lattice of charged particles, and their mutual repulsion gives structure and firmness. But the structure is mostly empty space. We and the world we live in are made of a whole lot of nothing. It's a humbling realization. You are a being composed almost entirely of voids, shaped by forces and energy into the form you call you. In a very literal way, you are a small universe of particles orbiting each other in vast fields of emptiness. Now we have explored the microscopic character of space, the quantum foam and the atomic void. We've seen that even when matter is present, it's built on a framework of emptiness, and even when nothing is present, space is still far from idle or empty. The calm void of night harbors deep activity at tiny scales and comprises the majority of the volume of any solid thing. Space pervades every corner of existence. It is above us in the cosmos and within us in each atom. Let's step back out to the cosmic scale again. We've marveled at gravity and quantum foam and the space within atoms. But what about the shape of the universe as a whole? Does this infinite darkness go on forever? Does it curve back on itself like the surface of a planet? These questions have intrigued humanity for as long as we've looked up and wondered. Is space infinite, or is there some kind of boundary or loop? With modern science, we have attempted to measure the geometry of the universe. The answer isn't fully in, but so far it appears that on the larger scales we can observe, space is extremely flat and likely unbounded. By flat, we mean it follows the rules of Euclidean geometry, the sums of angles in triangles, etc., as far as we can see. If space had a noticeable curvature, we would detect distortions in the patterns of galaxies or the light from the early universe. The results? All measurements indicate that space is extraordinarily flat on the biggest scales. If there is curvature, it is so gentle that our observable universe, a sphere of about 93 billion light-years in diameter, doesn't reveal it. To use an analogy, Earth appears flat to someone walking a few miles because it's so large that the curvature isn't obvious at that scale. Similarly, the universe might be curved in some way, but on the scale we can survey, it looks effectively flat. What does flatness imply for the extent of space? It suggests that space could be infinite, extending forever in all directions, or it could be finite, but without boundary, like how the 2D surface of a sphere is finite area, yet has no edge, except extended to three-dimensional space. If space has positive curvature, like a 3D sphere, it would be finite in volume, and if you traveled far enough in one direction, you might eventually end up where you started, just as an ant crawling on a basketball eventually loops around. If space has negative curvature, like a saddle shape, it would be infinite and spread out with a different geometry. A flat universe, the simplest case, can be infinite and just go on and on. Current data lean toward flatness and therefore possibly infinitude, or a curvature radius so immense that for all intents and purposes it is infinite to us. From what we can tell, there is no edge to space, no wall where space ends. If it is finite and curved back on itself, going in a straight line could, in theory, bring you back to your starting point after an almost inconceivably long journey. We have looked for evidence of light wrapping around the universe, like seeing the same galaxies repeated from opposite directions, which could happen if space were closed and not too large. But we haven't found any such patterns. If the universe is finite and closed, it's far larger than the volume we can see. If it's infinite and open, it just has no end. In either case, there's no boundary that says, beyond here, there is nothing. Space, as far as we know, either goes on forever or loops back on itself. The observable part, what we can see, is certainly finite, but that's only due to the limited age of the universe and the finite speed of light. Beyond that observable horizon, we expect there is more universe, probably much more. We can summarize our findings here. The large-scale universe appears flat and unbounded. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, by satellites and telescopes have narrowed any possible curvature to be extremely slight. So, space is remarkably flat as best we can tell. It might truly be infinite. It might wrap around on a scale so huge we haven't detected it. Either way, for our observable domain, Euclid's geometry holds to a high degree. Parallel light beams do not meet, and the angles of a huge triangle drawn by, say, beams of light spanning billions of light years seem to add up to 180 degrees. This is a clue that the cosmos, on the whole, is not shaped like a sharp sphere or saddle within our view. If it is spherical, the sphere is enormous beyond imagination. If it is saddle-like, the curvature is so subtle that we haven't discerned it yet. In our contemplative journey, lying here under the night sky, it's awe-inspiring to realize we've been able to figure this out at all. By observing distant galaxies and the patterns in the microwave background, humanity has effectively used the universe itself as a giant ruler and protractor. We map the distribution of galaxies and notice that on large scales, they form a sort of cosmic web, filaments of clusters and superclusters surrounding huge, nearly empty voids. Those voids, expanses tens of millions of light years across with hardly any galaxies, highlight again how dominant space is over matter. Matter forms a delicate lace, and space is the vast expanse between its threads. The cosmic web shows that even on the grandest scale of clusters of galaxies, emptiness stretches out between them, making up the bulk of existence. Indeed, when astronomers survey the cosmos, they see that galaxies are not evenly spread. They line up in filaments and walls, with enormous voids between. Those voids are truly empty regions, aside from perhaps the stray hydrogen atom here or there. Some voids span hundreds of millions of light years with essentially no galaxies inside. Think about that. Such a volume is mind-bogglingly large, and yet nearly completely devoid of stars, planets, or light. Just tenuous gas and darkness. Those cosmic voids are, in a sense, pure space on the largest scale, a testament to how predominant emptiness is. The luminous matter, galaxies, clusters, outlines like scaffolding on the tapestry of space, but the vast gulfs between that scaffolding are space itself, pristine and quiet. Now, our understanding of space wouldn't be complete without touching on one of the greatest mysteries of the cosmos today, the fact that the universe's expansion is speeding up. We mentioned earlier that the universe is expanding like a rising loaf of bread, carrying raisins, galaxies, apart. You might expect, intuitively, that this expansion would slow down over time. After all, gravity is pulling galaxies toward each other. Indeed, for a long while after the Big Bang, the expansion did slow as gravity reined it in. But to astronomers' astonishment, in the last few billion years, the expansion has begun to accelerate. Galaxies are flying apart faster and faster. There is something in space, some form of energy tied to the vacuum itself, that is pushing the universe outward. We call this strange phenomenon dark energy. The name is just a placeholder, really, a label for our ignorance. It was discovered in the late 1990s when two independent teams observed distant exploding stars, supernovae, and found them dimmer, and thus farther, than expected. It was as if, over the billions of years their light traveled, the space between us and those supernovae had stretched more than it would have in a decelerating universe. At first, this result was met with surprise and a bit of skepticism. Could the expansion be accelerating? That was contrary to everything we thought. Even Einstein, long before, had considered a static, or at most slowing universe. But one by one, other evidence accumulated. Detailed maps of the cosmic microwave background and surveys of galaxy clustering both pointed to the same conclusion. Some kind of repulsive effect is at work on cosmic scales. By the early 2000s, the verdict was clear. The expansion of the universe is speeding up. So what is dark energy? In short, we don't know. It appears to behave like an intrinsic property of space. Like each cubic meter of vacuum has a certain tiny amount of energy that doesn't dilute even as the universe expands. If that's true, then as space expands, you get more vacuum, and thus more of this energy, causing expansion to push even harder, a runaway effect, though fortunately a very gradual runaway. Roughly 2/3 of the universe's total energy content today seems to be this dark energy. Only about 1/3 is in matter, mostly dark matter, plus a few percent normal matter like atoms. That means most of what's out there is this mysterious energy of empty space. It's dark because we can't see it or touch it. It doesn't emit light. And it's energy in the sense that it does work on the universe. It's causing space to swell. We sometimes describe dark energy as a negative pressure or an anti-gravity effect of the vacuum. It's as if emptiness itself has a springiness, a tendency to expand. Every bit of empty space gently pushes outward on itself. The effect is extremely weak on small scales. It's completely overwhelmed by local gravity or even the forces binding galaxies. But on the vast scale where gravity's pull has been growing weaker as galaxies get farther apart, eventually this subtle pressure took over and started accelerating the expansion again. The concept of dark energy reminds us how much we still don't know. It humbles us. We see its effects, yet the cause remains elusive. It could be something fundamental about space that we have yet to understand, perhaps related to that quantum foam energy we talked about. Those straightforward calculations of vacuum energy don't match the observed dark energy. That's a huge puzzle in physics. It could be a new field or fluid pervading the cosmos, or an adjustment needed in our theory of gravity at large scales. We gave it a name, but naming is not understanding. Dark energy is truly a question mark at the heart of cosmology. In essence, what we know is this: empty space isn't just inert nothing. It has this property that is making the universe fly apart faster and faster. The same emptiness between galaxies carries an unknown energy that currently drives the fate of the entire universe. Far from being an irrelevant void, space, through dark energy, will determine how the cosmos evolves trillions of years into the future. To put it succinctly, something latent in empty space, call it dark energy, is accelerating the expansion. The void has a sort of built-in push. This discovery is as dramatic as when we first learned space can bend. It tells us that space has a mind of its own, so to speak, a propensity not only to warp when mass is present, but to grow even where mass is absent. It's as though emptiness has a gentle heartbeat, steadily pumping the universe larger. So now we have seen space from two extreme perspectives: the microscopic, roiling with quantum fluctuations, and the cosmic, swelling with dark energy. We've also seen space permeating matter in atoms. It is clear that space is not a passive backdrop. It's dynamic and rich. Let's recap our journey so far in simpler terms. Gravity taught us that space is flexible. It can bend, fold, and ripple. Relativity taught us that space and time are united. Quantum physics taught us that space is restless at small scales. It's never truly empty. Modern cosmology taught us that space can expand and carries a mysterious energy in its very form. And everyday life and atomic physics taught us that even seemingly solid matter is mostly space inside. Now, with these insights, consider what space really is. It's not empty. It's the very medium of existence. Space is the canvas on which the masterpiece of the night sky is painted, and also the paint and pigments in that masterpiece. It is the medium through which light travels, and also an actor that shapes the story. By bending light, for example, as in gravitational lensing, where space curves around a massive galaxy cluster and bends the light of more distant galaxies into arcs. Space is the connector between distant objects, the silence that allows a conversation via light or gravity to happen across cosmic distances. Space is the stage on which all cosmic drama unfolds, and yet it is also an actor, shaping the plot with its curves and expansions. It is the ocean on which galaxies sail and the gentle tide that carries them apart. Space is a teacher of humility. It shows us that even what seems empty can hold unimaginable power and significance. It reminds us that absence can be potent, that silence can speak volumes. The stillness of space, which once seemed like nothingness, in fact contains the code that dictates the evolution of the entire universe. When we consider the scale of space and how much of everything is made of it, we might feel small, but there is comfort in it too. Space is a comfort in its constancy. It's been here since the beginning and will be here long after the end of all things. When we feel overwhelmed by our day, we can look up and remember how vast and enduring the universe is. Our worries shrink in the face of that perspective, not to trivialize them, but to soothe us with the knowledge that we're part of something much larger and older, where many troubles have come and gone under the eternal sky. Even our ignorance, like the mystery of dark energy, is a kind of tribute to how subtle and profound space is. It's astonishing to realize that only a century ago, we didn't know any of this. We thought the Milky Way was the entire universe, and we believed space was just an empty void that played little role. Now we've learned so much, that the universe is expanding, that space and time bend, that there are countless other galaxies, that space can erupt with virtual particles and drive cosmic acceleration. Each discovery has only deepened the wonder. Knowing that space can ripple and boil and propel galaxies doesn't take away the magic of the night sky. It adds layers of awe to it. The more we comprehend, the more we appreciate how extraordinary it all is. Finally, let's ponder one more speculation that stretches our imagination to the limit. The possibility that our universe's space is not the only space. Could it be that beyond the observable universe, or in dimensions or contexts we cannot see, there are other universes, other expanses of space-time, disconnected from ours? In other words, a multiverse. This idea is highly speculative, yet many scientists consider it plausible given certain interpretations of cosmology and quantum theory. One scenario arises from cosmic inflation, the extremely rapid expansion that likely occurred fractions of a second after the Big Bang. Inflation might not have ended everywhere at once. It could be bubbling continuously, even today, in distant realms beyond our horizon. Each bubble that inflation drops out would become its own universe with possibly different properties. Our universe would be one bubble among potentially countless others in a frothing metacosmos. To visualize this, imagine stepping outside our universe, a mind-bending thought, and looking at a larger sphere of reality. You might see an eternally expanding space like boiling water, with bubbles forming here and there. Each bubble is a universe, perhaps with its own galaxies and laws of physics. Ours is just one bubble that happened to inflate and then slow down, allowing stars and galaxies to form. Some bubbles might remain forever separate, carried away by relentless inflation in between. Others might occasionally collide, potentially leaving subtle imprints. People have even searched our sky for patterns that could be from a collision with another universe bubble, though none has been confirmed. In this view, reality is far grander than what we can see, a multiverse of universes. Another multiverse concept comes from quantum mechanics, the many worlds idea, where every quantum event splits reality into multiple branches. In that interpretation, there is a vast ensemble of parallel outcomes, parallel universes coexisting in a larger quantum reality. If true, There might be another version of you in a parallel world where some decision or event went differently. This is a different flavor of multiverse, more about layers of reality stacking on the same space rather than separate bubbles of space. But it underscores how space might be part of a much larger tapestry. Whether through cosmic inflation or quantum many worlds or other ideas, like perhaps a cyclic universe that periodically resets, the multiverse remains a hypothesis. We have no direct evidence of other universes. We may never have. It is a mind-expanding possibility, essentially suggesting that what we used to call the universe, meaning everything, might be just a tiny piece of an even vaster existence. If it's true, it's the ultimate Copernican revolution. Not only are we not the center of the universe, but our universe might not be the only one of its kind. Just one bubble in an endless foam. Such a concept can be daunting, but it can also be oddly comforting. It would mean creation is endlessly fertile. That reality tries every possibility, that somewhere, everything that can happen does happen. It also could provide an answer to that question of why our universe has the conditions it does, why the constants of nature are fine-tuned for life. If there are countless universes with varying conditions, we naturally find ourselves in one of the rare universes that is compatible with observers like us. In a multiverse, our hospitable cosmos isn't a 1 in a billion fluke so much as an inevitability among infinite tries. We should stress that the multiverse is still speculative. It's an idea, albeit one that arises from serious physics theories, but we have yet to find a way to test or observe it. It remains a tantalizing possibility on the fringes of our understanding. Whether true or not, just contemplating it broadens our perspective even further. It tells us that space, that fundamental thing we've been exploring, might come in an endless variety of forms across different universes. Perhaps some universes have more dimensions of space, or different kinds of particles, or maybe no matter at all, just endless empty space-time, expanding or contracting. The possibilities are endless. Even if the multiverse remains unproven, thinking about it does one certain good. It underscores just how precious our particular universe is. We have this vast cosmos to explore and understand, full of wonders like those we've discussed tonight. We might be essentially alone, with no other universes ever reachable, or we might be one among billions. Either way, our task and our joy is to know our universe as deeply as we can and find our meaning within it. Now, let us gently return to where we began, to the simple stillness of the night and the feeling of space around us. After journeying through curved space-time and quantum foam, across the cosmos and into the atom, we come back to ourselves, lying here under the sky, whether literally or in our mind's eye, quiet, at peace, and maybe a little wiser. The night is still as it was, but we are not the same. The darkness holds more meaning now. We can sense, behind the silence, the faint echoes of all those phenomena we've talked about. The whisper of space-time, the hum of the quantum vacuum, the faint pressure of dark energy, the quiet spaciousness within our very cells. The stillness around us resonates with the knowledge that it is not an empty stillness at all, but full of structure and story. Space is not empty. It's imbued with the fabric of existence. It connects everything to everything else. In this darkness, the light from distant stars travels. The space allows it to move at the fastest speed possible. The gravity of the Earth extends through space to tug on the moon. Fields, like the electromagnetic field, permeate space and allow radio waves, visible light, X-rays, all forms of light to propagate. Invisible geomagnetic fields from Earth reach out into space around you right now. Space truly is the medium in which all things exist, and through which all interactions occur. If it were somehow removed, all those interactions would vanish, and nothing could happen or even be. Consider some of the roles of space we've encountered. Space is the canvas on which galaxies paint their grand designs, and also the weaver that curves and folds itself to create gravity's effect. Space is the nurturer of structure. Its quantum fluctuations seeded galaxies, and its expanses gave them room to grow. Space is the arena of all history. Every event that has ever happened, from the birth of a star to the firing of a neuron in your brain, took place in space-time. Space is the ultimate connector. When you touch a loved one's hand, it's the space and electromagnetic force fields in that space, between the atoms of your hand and theirs, that communicates the pressure and warmth. Space is a teacher. It teaches us that what appears empty can be full, that absence can have presence. It is a guardian of the universe's secrets, hiding dark energy within itself, keeping the ultimate fate of the cosmos in its hands. And space will be the stage for the universe's far future. Looking trillions of years ahead, one can envision a time when space will be virtually all that remains. As the eons pass, galaxies outside our local group will drift farther and farther away, eventually vanishing beyond the horizon, their light stretched into oblivion by the expanding space. The night sky will grow emptier as distant stars disappear from view. Trillions of years from now, even the stars in our own galaxy will exhaust their fuel. One by one, they will wink out, leaving behind faint embers, white dwarfs, neutron stars, and black holes. These remnants will gradually cool and evaporate, in the case of black holes, via Hawking radiation, over an incomprehensible span of time. The universe will continue to expand and cool toward a state of almost complete darkness. In that far future, no new stars are born. No bright galaxies light up the sky. What remains is largely space itself. Vast, cold, nearly empty, studded only sparsely with subatomic particles and the fading whisper of photons from long ago starlight. And yet, through it all, space endures. The same fabric of space-time that was there at the fiery birth of the cosmos will still be there in that silent twilight eons hence. The stage persists even after the actors have left. Perhaps that will be the final chapter of our universe. An ever-expanding dark volume of nearly pure space, quietly extending into eternity. Perhaps, someday, quantum fluctuations within that nothingness might seed a new Big Bang, a new universe, a speculation in some cyclic cosmologies. But either way, the legacy of space is that it is the last cosmic witness. When all else has come and gone, space will still be here, silent and waiting, as it was in the beginning. Space is, in a sense, the alpha and omega of the universe, present at the start, shaping everything in between, and remaining at the end. Now, back to this moment. The night is deep and beautiful. The quiet around you, this gentle void, is the same entity we've been contemplating in all those extraordinary ways. Let that sink in. The empty air and space enfolding you right now carries the heritage of the entire cosmos. It carries the gravity that holds you to Earth. It carries the starlight that reaches your eyes. It carries the potential for future worlds and the echo of the very birth of the universe, a faint whisper of microwave background that bathes all of space, even now, at about 2.7 degrees above absolute zero, giving the night a slight warmth. This space around you is part of the same continuum that bends around a black hole and expands between galaxies and buzzes with vacuum energy. You are deeply connected to the universe through space. You always have been. It's impossible to be truly isolated because the fabric of space links you to the furthest galaxy and the smallest atom. When you look at the stars or simply breathe the night air, that connection only becomes more apparent. You are a child of space, born from stardust that coalesced in space, sustained every second by the oxygen and photons traveling through space. And ultimately, when you return to dust, your particles will drift in space again. Bask in that realization. You belong. You belong here in the universe, and it belongs in you. The boundary between you and out there is not a wall, but a porous membrane constantly exchanging matter and energy. You inhale the atmosphere, drawing in molecules that might once have been exhaled by ancient trees or dinosaurs, and ultimately originated in cosmic processes. You exhale, and your breath's atoms eventually mix into the sky and beyond. In a physical sense, you are never separate from the universe. You are always in communion with it. Take another slow, gentle breath. Feel the cool air fill your lungs, and know that even that simple act is an interaction with space. As the air spreads in your lungs, it's essentially molecules finding room in the internal space of your body, delivering oxygen to your cells across microscopic gaps. As you breathe out, you're releasing carbon dioxide that will travel through the atmosphere, maybe feed plants, maybe one day waft into the upper sky and beyond. Through you, the earth and space are linked. Now, you have permission to let go of all these thoughts if you wish. You don't need to actively think about curvature or quantum foam or dark energy anymore tonight. The knowledge is there, settled gently in the back of your mind, enriching the way you feel the night. You can simply relax in the feeling of it, the feeling of being part of this vast, ongoing cosmos. Above, the stars continue to shine, distant and silent. Around, the darkness remains calm and embracing. You might sense in your own body a mirror of the cosmos, the rise and fall of your chest like the expansion of space, the circulation of blood like galaxies drifting in their clusters, the neural flashes in your brain like tiny starbursts. In the stillness, you can almost feel the subtle humming connection between your life and the wider universe. You are safe. You are weightless and free. The quiet of space enfolds you like a warm blanket. Feel how the whole universe supports you in this moment. The ground beneath you, the air around you, the sky above. You belong here. You are part of all this. There is nothing you need to do right now except be. Just exist. Just rest. Inhale the stillness. Exhale any worry. Let yourself float on the calm of the cosmic ocean. You are safe. You are embraced by existence. You are at peace. No matter where you go, you carry this home of space with you. It was there at the first moment of your life. It sustains you each day, and it will remain long after we are gone. The stillness that surrounds you is the same stillness that cradled the young universe and that will hold the final stars as they wink out. You are truly home in this stillness. It is the cradle of everything. All the understanding we've gained about gravity, time, quantum foam, expansion, and so on, leads to a simple, profound truth. Space is not empty. It is everything. It is the foundation and framework of existence, and you are not separate from it. You are one with it. An expression of the universe, a part of space becomes self-aware. When you gaze at the night, the universe is gazing back at itself through your eyes. So rest now, gently, in the embrace of space. Feel the deep peace of knowing that you are held by the same darkness that carries the stars. The infinite extends around you, quiet and caring. Let go of any remaining tension. Let it fall into the vast well of calm that is space. Let your thoughts drift like gentle clouds across the sky of your mind. No need to chase them. They can float away into the darkness, leaving you calm and clear. You are safe. You are weightless. You are free. The endless silent universe enfolds you, and you belong to it. You are a part of it all, and it is a part of you. In this profound unity, you can release all fears and rest. The night is very quiet now. Around you, the earth sleeps, and the cosmos watches in patient silence. Feel your heartbeat slowing, peaceful. A tiny clock kept by space-time within you. Feel your breaths becoming soft and rhythmic, the same rhythm that pervades all of nature. There is no rush. Time flows at its own gentle pace. Space provides limitless room for your dreams to unfold. You are home in the universe. You are never alone. The space that fills your room, your lungs, and your heart connects you to the furthest galaxy and to the beginning of time. In this knowledge, you can truly rest. All is tranquil. All is as it should be. Stillness. The stars shine. The galaxy slowly turns. The universe breathes in and out on timescales far beyond comprehension. And here, in this quiet moment, you breathe softly, in unison with the cosmos. The stillness of space is within you and around you. Let it lull you into a deep and gentle sleep. Feel yourself drifting, weightless, on a calm, cosmic sea. There is nothing to fear in this dark. It is the same darkness that gave birth to the first dawn. There is everything to love in this silence. It carries the echoes of creation and the promise of eternity. You are safe. You are connected. You are at peace. Sink deeper now into the comforting dark. The universe holds you like a parent cradling a child. The ground beneath you, the sky above, all is one with you. Your mind is quiet, tracing the outlines of these truths with a final, drowsy sense of awe. What remains is not calculation or analysis, but a simple reverence for existence. In the grand sanctuary of space, you close your eyes, your breathing slow and steady. The boundary between yourself and the night dissolves. You are the universe, and the universe is you, a wave returning to the ocean of space. Rest now in that knowledge. Rest in the arms of the cosmos. Feel the profound stillness, the gentle, omnipresent support of space beneath you, holding you up as it has held up worlds and suns and galaxies. Let that stillness fill you. There is nothing more to do, no more striving needed. Just be. Just let yourself go, like a leaf floating on a vast dark pond, carried by the calm currents. Space will watch over you. It has always watched over everything. Your mind is calm. Your body is relaxed. The stars continue their silent vigil overhead, and you drift closer to sleep, carried by the same silence that spans the light years. The feeling of space, that stillness, that openness, that gentle cradle of all things is all around you, and it soaks into your very bones. In this moment, you are that stillness. There is no separation. Quietly, the universe whispers you a lullaby in the language of silence. It says, "You are home. You are home." Let yourself drift in this infinite peace, stillness, silence, space. The journey is complete. The knowledge is within you. The stillness is everything. You are a child of the cosmos, and the cosmos is kind. Feel its love in the quiet of the night. Space is not empty. Space is everything. And you, your atoms, your mind, your life, you are part of that everything. You always have been and always will be. In the great dark between the stars, there is comfort and belonging. In the stillness here, there is the embrace of the infinite. Be at peace, dear traveler of the universe. You are home in the stars and the night. The space around you is your space. The silence around you is your silence. Nothing separates you from the whole. You are safe. You are loved. You are one with the deep, eternal stillness of space. Rest now in that eternal stillness. Let the quiet carry you into restful sleep, as gently as a mother rocks a baby, as naturally as night becomes dawn. The universe holds you. Stillness, silence, sleep. Good night, child of space. The cosmos within and around you watches over you, now and always. Stillness, silence, darkness. No stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. The black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things? Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore. Yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. The space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years, this expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, two initially parallel beams of light would eventually converge and meet, and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, after the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint, ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us, accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away. What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness. For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view, the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, and now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface, back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, you are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here, step by step. As you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere, ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales, far smaller than an atom, smaller than the tiniest subatomic particle? Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. Space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions, humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection in 2015 came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves. Black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space. We depend on it. We are composed of it. In a sense, we, conscious beings, are space's way of observing itself, the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things. It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it, we are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be. In the beginning, there was silence, a silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies, each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age, about 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light years in radius, beyond which the universe fades into an unknowable darkness. And yes, That horizon's radius is larger than 13.8 billion light-years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us. A view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball, there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling, an infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve, like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities. unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see and all that we cannot see was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others. Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water, each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow, and if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions, it fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties, suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe. And inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know, a sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist, and perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe, mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the Standard Model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water, yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all, it's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected. Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought. What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell space-time how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well, a constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist? And why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teems with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field-filling space, one that can vary from place to place or era to era, and whose properties we have yet to determine. Another wild possibility, perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy. For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up. And we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity, wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trapdoor. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, the tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time, you reach the central singularity and are crushed. your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of space-time, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon. We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding — we predicted them, then observed them — and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately, yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past, we anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics, ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states? Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars, but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons, one by one, through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality, the many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others. So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected. For example, two photons can be entangled in polarization such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus, their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory, confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer: it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme, perhaps in the subsurface oceans of icy moons like Europa, or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, but it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, and soon next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion, that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble, 100 light years in radius, and we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine. We'll find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale, inert matter becoming sentient, yet it happened. In us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states. For instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as FEF. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences. For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole, or with fundamental fields. These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us, because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions. Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism, the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, But that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed, though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces, the Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10 or 35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth, to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments, extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery and we respond with curiosity, a fundamentally human trait, perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes, telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory, a momentous achievement that could answer some of those questions, maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, Exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality. Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection. You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink, and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature, or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter. Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing, and then finding even more not knowing, is likely endless. And that is good. It means our descendants, be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, we'll go there, and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer: the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. The spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable. Yet none of those physical things inherently produce meaning. A star doesn't seek meaning. A galaxy doesn't appreciate beauty. But we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound. But there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, "There is more, so much more." It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle. But that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the Earth, perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game, and perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the Earth, a reminder that even the local theatre of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping space-time itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human. The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime. In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds, suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, why, how, what's beyond, or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life. That is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious. And it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive.